Okay, next I want to discuss random variables, and the main point I want to convey to you is that random variables are equal to functions. Indeed, a random variable x is a function from the sample space to some field, let's call it f, and this field can be either the integers or the reals or complex numbers, etc., etc. So in the case if this is this field is the integers, then we talk about integer random variable, a real random variable, a complex random variable, etc. Okay, so this means that for any omega that belongs to the sample space, this function associates a value x of omega that belongs to this field. Okay, so now because we have already defined a subset and an algebra of subsets of omega, and we have already defined the probability distribution over this set, we can define the probability distribution of a random variable So if f is a discrete set, then we will say that the probability that x of omega is equal to x is equal to p of x. Notice that this is a definition of p of x, because this is already an event that belongs to the algebra of events that we have defined. So this object is already defined, the probability of this event is already defined. So this is the definition of the probability distribution. For a continuous random variable, so for example, if our random variable is a real random variable, then you can think of events such as the probability that the random variable, the value of the random variable belongs to some interval AB, and I can define the probability density function as a function such that the integral from A to B of this probability density function, this is called probability density function. So this probability gives you the probability of this event. Okay. Of course, so you see that this definition is consistent with all the rules of probability that we have defined so far. So, for example, the probability that x belongs to either an interval or a disjoint interval will be the sum of the probabilities, so the sum of the integrals over these two disjoint intervals, and so on. Also, one defines the cumulative distribution of x, cumulative distribution as the probability that x of omega is less or equal to x and this defines this is defined in terms of the probability density as the integral from minus infinity to x of p of x prime. Okay, and I will also denote this with an uppercase P of x. Okay? So, there is an important fact to remember, that the cumulative distribution is a probability, so it is a number between 0 and 1. But the probability density, instead, is not a number between 0 and 1, because it has the dimension of 1 over x. Okay, so it's not a high-dimensional quantity. And this we realize when we want to change variables. So y, imagine that I define a random variable y, which is a function of another random variable x. And now imagine that I know what is the PDF of x, I want to know what is the PDF of y. Okay? And so imagine that we consider the case where f is a monotonously increasing function of x. Okay? So the idea is the following. So that if this is the function f of x, then essentially the definition of the probability density, if I take an infinitesimal interval between x and x plus dx here, so the probability that the random variable falls into this interval is p dx times dx. Okay? This is the probability that the random variable x falls into this interval. And this should be equal to the probability that the random variable y falls in the corresponding interval between y and y plus dy. Okay, so this must be equal to the probability of the random variable y to fall between y and y plus dy. Okay, where y should be equal to f of x. Okay? So you see from this definition that the probability, the PDF of y should be equal to the PDF of x divided by dx divided by dy. And what is this? Well, this is the inverse of, dy by dx. So, and this is exactly the first derivative of the function f at this point. Okay, so this is exactly px of x divided by the first derivative of x. Okay. Now, this is true for increasing function. So if we take instead a decreasing function, then you can see that so x and y, so the dy will be equal to minus the first derivative times dx. So in general, what I should do for a monotonous function, I should put the absolute value of the first derivative of x. And if you have a function which is more complicated, that is maxima and minima, or something like this, then you should consider that for a particular value of y, there will be different intervals in x. So the probability that y attains this value will be equal to the sum that the random variable x is equal to this, or this. So that you should, here x should be equal to f to the minus 1 of y, clearly. So in general, what you should do is to sum this term for all x which are equal to the f to the minus 1 of y. Okay, so on all these points. Okay. Very good. So, of course, you can generalize this definition of a random variable to, you can have more than one random variable. So you can have a vector of random variables, okay? And this is just, so each component will belong to, if you have a vector of real random variable, then each component of this vector will belong to this, will be a real number. And you can also define what is called the joint distribution. Or the joint PDF. And this you can define as PDX times for infinitesimal volume element dx. You can define this as being the probability that the random variable x belongs to this volume, which is, so if you want, each component should belong to the interval xi plus dxi for all components. Okay? So this is called the joint PDF, and again, this is a definition of the joint PDF. And now, if you you can also define, if you have a vector of random variables, you can also define what is the marginal distribution. Of one of the random variable, let's say x1. Okay, so the marginal distribution of, say, p1 of x will be the integral for dx2 dxn, or let's say d, let's say this, let's call n the from minus infinity to infinity of p of the joint distribution where the first random variable is equal to x, and the second one is x2, x3, xn. Okay? So, when you do this operation of integrating over all these random variables, this is equivalent to so if you want, this is equivalent to the total probability rule that we have already seen. So that you ask what is the probability of the event that x1 is close to x, and in order to obtain this, you take the probability that the vector is in a particular position, but then you sum over all the probability that x2, x3, xn. Okay? So this is called the marginal distribution. Of course, so say two random variables x1 and x2 are independent if and only if the joint distribution of this joint PDF of these two random variables is equal to the product of the marginals. Okay? So this is how you define independence for random variables. So independence of random variable means that the joint distribution is the product of the marginal distributions. Okay? And of course, this generalizes to any number of random variables. Okay? Likewise, you can also define the conditional distribution. The conditional PDF you can define the probability of a conditional distribution or probability density function as the probability of x1 given x2 as being so this should be the probability that x1 is in an interval between x1 and x1 plus dx1, and so this should be equal to the joint probability divided by the probability, the PDF of P of x2. Okay? So if you want, you can add a dx2 here and a dx2 here. So this would be the joint probability that x1 is the first random variable between x1 and x1 plus dx1, and the second is between the x2 and dx2 plus dx2, and you divide this by the probability that x2 is between x2 and x2 plus dx2. Okay? And so by this equation you see that you can define the joint PDF as the conditional PDF of x1 given x2 as the joint PDF divided by the marginal PDF of x2. Okay? So I'm sorry that in probability we are going to use the symbol P many times. But usually this does not, after you get used to it, this does not cause too much confusion, hopefully. Okay, so now let's make some examples of random variables, and let's start from the simplest ones. Okay, so the simplest one is just a binary random variable. A random variable x of omega that can take value, say, that is defined, say, on the sample space. This is a sample space, and in, say, half of this random space, the sample space has value 1, and the other half, in the other part, it has value 0. So, generally, you can define this random variable by its probability distribution. You can say that this random variable is equal to 1 with probability p, and is 0 with probability 1 minus p. Okay, so this is the simplest, where p is a number between 0 and 1. Okay, so now you can think of instead a little bit more complex case is the one of Bernoulli trials. So the idea is to compute, to consider a sequence of n binary random variables, and each of these is a binary random variable of this type that can take value 0 and 1, and all these are independent random variables. Okay. And so the variable we are interested in is Sn, which is the sum from 1 to n of the xr. So what is the meaning of this? So you can think at the value of these random variables as the indicator variable that tells you whether in a succession of trials, so the first, the second, etc., or the n trial give you a success. Success can be that a particular event occurs. There can be that, say, in a toss of a coin you have a head, or it can be anything. Okay, but once you define what is the event you are interested in, you can define a random variable which is this, which is 1 if this event occurs and 0 if it does not occur. And you can think of repeating this experiment under the same condition independently for n times. And then this random variable just counts the number of success. Okay? And so what we are interested in is to compute what is the probability that the number of success is equal to k. Now, because these random variables are independent, so the probability to have a k success is p to the power k, because each success has a probability p. The probability, but we will also have n minus k failures, so and these are probability n minus k. But then this success can occur in any possible order, and the number of possible orders that are there is n choose k. Okay, so this is the binomial distribution. Or the Bernoulli the Bernoulli distribution or binomial distribution. Okay, and okay, so the next interesting random variable that I want to remind you is the Poisson It's a Poisson random variable. And and this can be thought of imagining the same scheme of Bernoulli trials, but when n goes to infinity, but with p which goes to 0. Okay? So if you take the limit n goes to infinity with n times p being equal to lambda finite, then this equation here, you can see that this equation, so the limit as n goes to infinity with np equal to lambda of d of k of this expression here, well, let's do this limit in steps. So first of all, this part will be 1 minus lambda divided by n to the power n minus k. So when n goes to infinity, this converges to e to the minus lambda. Okay? So this term here is lambda divided by n to the power k. So here you will have a term lambda to the k times e to the minus lambda, which is this. And then you have n choose k divided 1 over n to the k. So this is n times n minus 1 times n minus k plus 1 divided by k factorial times n to the k. So you can figure out that when k is finite and n goes to infinity, this ratio here is going to 1. So this object is converging to 1, so you just have a k factorial that remains. So this is the Poisson distribution. So what is the meaning of the Poisson distribution? So the Poisson distribution is a distribution that we think which applies to events that are homogeneously distributed in some space. Okay. So, for example, if you think at a process that occurs in time, like, for example, a typical process is radioactive decay. So this is a process that the probability to observe a decay in any time interval dt is constant, is alpha times dt, and the probability that you have a decay at a particular time and a decay at a different time, these two events can be considered to a good approximation as independent. Then if we consider a particular time t, and we ask how many events occur in this interval, then we are exactly in the situation of Bernoulli trials, because for any infinitesimal interval there is a probability that this event occurs. And if the interval is really infinitesimally small, either the event occurs or it does not, its probability is proportional to alpha dt. So we are exactly in this situation. And if you are interested in an n times p, if this time is equal to t, is exactly equal to alpha times t, which is lambda. And this is fine because the probability is alpha times dt, and the number of intervals is t divided by dt. Okay, and so so in this case you find this Poisson distribution with this. But you can also think of, say, other things, like, say, if you look at points distributed at random in a volume, for example. So imagine that you think of a cake, and this cake contains some candies, and if you assume that in each volume of this cake, in each small volume of this cake, there is the same probability alpha times dV that you find a candy, then the probability that there will be k candies in the cake will be given by Poisson distribution with this lambda given by alpha times the volume of the cake. Okay, by exactly the same argument. Okay, so the next distribution that I want to discuss is a distribution that will be very, very important, and is the Gaussian distribution. So the Gaussian distribution is given by, so we have a random variable, a real random variable, and its PDF is given by 1 over the square root of 2 pi times sigma e to the minus mx minus m squared divided by 2 sigma squared. Okay? And I encourage you to verify that this is the correct normalization for this distribution. Of course, the integral from minus infinity to infinity dx of p of x, this must be equal to 1. Okay, this is it's called the normalization. And we did last time, we discussed last time how to do a Gaussian integral of the form e to the minus something squared divided by 2. So I'm sure that you can do also this integral and verify that you get exactly 1. Okay, so there are two important things that I want to remind you of for the Gaussian distribution is that if you take n very, very large, then the binomial distribution is well approximated by 1 over the square root of 2 pi n p times 1 minus p times e to the minus 1/2 k minus np squared divided by 2np 1 minus p. Okay, so this is called the Moivre-Laplace limit of the Bernoulli distribution, and what it tells you is that this random variable n, Sn, when n goes to infinity, when asymptotically when n goes to infinity, converges where I will discuss what convergence means, but it's essentially given by a Gaussian distribution, a Gaussian random variable, with parameter m, which is equal to np, and parameter sigma, which is given by the square root of np times 1 minus p. Okay, and please verify this statement by using a Stirling approximation of n factorial. Okay, it's a bit lengthy calculation, but at least once in your lifetime you should do this. Okay, so the second thing I want to tell you about the Gaussian distribution is that it also generalizes to a vector of random variables. Let's say RT. And in this case, the joint probability distribution of this vector of random variables is given by the square root of the determinant of A, where A is a positive definite matrix, divided by 2 pi to the d times the exponential of 1 minus 1/2 m by, let's say, x minus m transpose times A times x minus m. Okay, where this m is a real vector and this matrix A is a positive definite matrix, which means a matrix which is symmetric and has all positive eigenvalues. And m is also a real number, a real vector in R to the d. Okay, so as an exercise, I also ask you to check that this is the right normalization for this function. That is, we have the integral in dx over all the space of p of x is equal to 1. And the way to do this is to, because A is a symmetric and positive definite, you can make a change of variable when you compute this integral, when you rotate to the space of eigenvectors of this matrix, and then you will see that the integrals factorize, and for each of the integrals you can use the integral that you did before, and you can also use the relation that the determinant of a matrix A is the product of its eigenvalues. Okay? Okay, very good. So the next random variable. So the reason why the Gaussian distribution will be very, very important and play a very special role is because of the Gaussian of the central limit theorem, as we will see. But there is another random variable which is very, very important, which is the uniform random variable. So the uniform random variable is a random variable which is defined in the unit interval, and is PDF is equal to 1 if x is in 0, 1 is equal to 0 otherwise. Okay, so it's PDF. If you plot it, whenever you do a numerical simulation, the random variables, the pseudo-random variables that you get from your computer, are generally distributed in this way. Okay. Then, of course, probably with more advanced software like MATLAB, you can also get random variables which have Gaussian distribution or other distributions. But generally, they are all derived from random variables that are distributed in this way, pseudo-random variables that are distributed in this way. And the idea of so that there is an important fact that allows you to compute, to draw random variables from uniform random variables, which is the following, that say for any random variables x of omega with PDF E of x, if you consider the following integral, then this is a uniform random variable. Let me call it U of omega. Okay? So this is, let me call it Y of omega. Okay? So this random variable is uniform. Okay? So this tells you that if you want to generate a random variable x which has a certain distribution P of x, you have to invert this relation and get x as a function of y, because then you can draw a uniform random variable and then you can compute the random variable x. Okay? And so there is a very interesting discussion of how to generate random variables, which is in a book of numerical recipes that I really recommend you to read, because, well, there was a famous scientist that said that whoever ever draws a random variable or a pseudo-random variable from a computer is in a state of sin. So it is good, it is important to know what is the particular sin that we are committing when we draw random variables. Okay, so the next random variable I want to talk about is the exponential random variable. Exponential distribution. So it's a random variable that is defined on the positive real axis, and it has a probability distribution which is equal to say lambda e to the minus lambda times x if x is positive and is 0 otherwise. Okay, so its PDF is given by something like this. Okay. Now let me first show you, for example, how you apply this rule in order to draw an exponential random variable. Okay, so in this case, so this is the integral from 0 to x of omega of dx lambda e to the minus lambda x. So this is just 1 minus e to the minus lambda times x of omega. Okay, so now if you want an exponential unknown variable, you have to invert this relation, which tells you that x of omega will be equal to minus 1 over lambda times the logarithm of 1 minus a uniform random variable. But of course 1 minus a uniform random variable is also a uniform random variable, so you can just write it as 1 over lambda times log of y of omega. Okay, so this tells you that if you want to generate this random variable which has this distribution, then you can draw a random variable which is uniform between 0 and 1, take the logarithm, divide by 1 over lambda, change the sign, and you are there. Okay, so the second thing that I want to tell you about exponential random variables is that these are very, very important for waiting times. Okay, it's a waiting time distribution. Okay, so what is a waiting time? Well, a waiting time is what you expect a waiting time is. So imagine that this is time, this is now, and imagine that you want to understand how much time you have to wait for the occurrence of a particular event. Okay, and this event, imagine that it is a probability of occurrence in each interval, which is the same, and is proportional, let's say, to lambda times the length of the interval dt, and the occurrence in each interval is independent of the occurrence in any other interval. Okay, so we already know that the probability. So if we call t of omega the time you have to wait, that is the waiting time, then the probability that t of omega is larger than t, so is the probability that no event occurs between time 0 and time t. Okay? And this is exactly the probability. If the number, we said the number of events that occurs in this time interval t has a distribution which is given by the Poisson distribution. So this is the probability that a Poisson random variable has value 0. Okay, so this is just e to the minus lambda times t. Okay, but these should be equal to the integral between t and infinity of the PDF. So if you take a derivative of this, then you find that the probability distribution P of x is exactly given by this. Okay? So this is the waiting time. This is the exponential is the distribution of waiting times when you are considering events that occur at random with a probability and independently with a probability that is constant in time. Probability being constant in time means that there is time translation invariance. Okay, so So this probability distribution, exponential probability distribution, encodes this time translation invariance and the independence of the events. So the fact that events are independent means that this distribution describes events that carry no memory. Okay? So to give you a sense of what this means, let me take a specific example. So imagine that we are interested in the time you have to wait for the next bus. So imagine that you arrive at this point in time and you want to take the bus. And imagine that the arrival of the bus in every time interval has the same probability and that there are independent events for any interval. Okay? Now imagine that you arrive to the bus stop and you ask yourself, and you ask to another person who is there, how much time ago, how much have you been waiting, okay? So imagine that this guy tells you that he has already been waiting tau minutes, okay? So then does this change the probability that you will have to wait t minutes more or not, okay? So in order to ask this question, so essentially from the point of view of this guy, this is the same question as asking whether his waiting time should be larger than t plus tau, given that we know that the waiting time is larger than tau. Okay. Now you can compute this probability with the rules of conditional probability. So this is just the probability of the joint event, this event and this event. But of course, this event is contained in this event, because if I wait this much, for sure I have to wait this much. Okay. And so this is just the probability that the waiting time is larger than t plus tau, divided by the probability that the waiting time is larger than tau, which is what I know. Okay? And then if I take this expression here, you see that this is e to the minus lambda t plus tau divided by e to the minus lambda times tau. So this and this go away, you just get e to the minus lambda t. So it tells you, this tells you that knowing what has happened before doesn't change at all the likelihood that an event will occur in the future. Okay? So this is a precise statement that telling you that this probability distribution encodes the lack of memory. So a process that does not carry any memory about past events. Okay, so the last thing that I want to remind you is about expectations. So how we define the expected value. So we define the expected value of a random variable x as the integral in dx of p of x times x. Okay, so it's just the product of the probability times the random variable summed over all possible values. So this is for a continuous random variable, for a discrete random variable that is defined on a certain set, let's call it chi. This will be p of x times x. Okay, and of course you can define the expected value for any function of a random variable, and this would be just the integral dx of p of x times f of x. Okay, and very good. So in particular, the expected value is a linear operator. So because the integral is linear, so if you take expected value of alpha x1 plus beta times x2, then this will be equal to alpha times expected value of x1 plus beta times expected value of x2. And also the other thing that we are going to use, that if x1 and x2 are two independent random variables, then the expected value of x1, x2 is equal to the expected value of x1 times the expected value of x2. Okay? Because, well, this is defined just as the integral dx1, dx2, dx1, dx2 of p of x1, x2 times x1 times x2. But if the two random variables are independent, then the joint distribution is the product of the two marginal distributions, and you can factorize these two integrals. And one gives you expected value of x1, and one gives you the expected value of x2. Okay? Very good. So now there are special functions for which are particularly used in probability and statistics, and these are called moments. This is just so the expected value of x to the n, let's say mn, is called the nth moment of the random variable x or of the distribution p of x. And in particular, the first moment is called the mean, and so m1 is the expected value of x, and gives you a quantitative idea of what is the typical value of x. But besides this, you would also like So if you have a distribution with a particular shape like this one, then this is x and this is p of x. The first moment will give you, well, in this case it will be a little bit not on the maximum. the first moment will give you an idea of what is the value you can expect from this random variable. But you would also like to have an idea of how uncertain are you about this estimate. So for this, you compute the variance. The variance of a random variable is just the expected value of x minus the expected value of x squared average. Okay, so in particular the standard deviation, which is the square root of the variance of x, gives you an idea of how wide is, how big is the uncertainty around the expected value. And in this way you can also define other things like tell you how asymmetric is this distribution, and this is given by the skewness, which is essentially the expected value of x minus expected value of x cube divided by the variance of x to the 3/2. Okay, this number, it's a number that if it is 0, you have a symmetric distribution around it's sort of an indication of a symmetric distribution about the expected value. If it is non-zero, then it tells you whether how big is the asymmetry. And like this, you can also define the kurtosis and other statistics. So the last thing I want to point out is that when you consider more than one random variable, you can also define the covariance of this random variable. This is exactly tells you how these two random variables co-vary. So, and this is given by this expression. So, so for example, if a random variable has a positive deviation around its expected value, and the second one also generally it also has a positive deviation around its expected value, when this is a positive deviation, then you will have a positive covariance that tells you that these two random variables move together, essentially. And when the covariance is negative, instead these two random variables sort of move in opposite directions. Of course, if x1 is independent from x2, then the covariance of x1 and x2 is equal to 0, because you can factorize this this expected value, and then each of the two terms, the two factors, is equal to 0. Okay, so the converse is generally not true, but it's true only if x1 and x2 are Gaussian. So the fact that the covariance is 0 does not mean that the two random variables are independent unless they are Gaussian. Okay? So the covariance is a measure of stochastic dependence, but it's not a good measure. We will we will discuss in the second part of the course a better measure of stochastic independence, which is essentially the mutual information. Okay, and but it's important to remark that unless you are sure your random variable is Gaussian, so having zero covariance does not mean independence. Okay.